we start off with Unit 6A, which will talk about fluid statics. Fluids are special kinds of materials which demonstrate the characteristic of flowing. So you all know what it means for a substance to flow. And in general, you can think of fluids as being liquids or gases. They take the shape of their container. When you push on one end of a fluid, it flows to the other end of a container, and that's the basic idea of fluids. And one of the most important ideas that we'll need to learn about is pressure. Pressure does not only exist in gases, but pressure also exists in fluids. And as a reminder, pressure is a force that is exerted over an area. And so if we have a fluid like this water contained right here in this tank, we can think about the pressure that is felt when we go deeper and deeper into the fluid. Many of you marine science majors will probably find the fluid stuff very interesting. That's why we will be spending the next 3 weeks on fluids. Quite a lot of fluids to be dealt with, but also you medical majors can think about blood flowing through veins or air filling up lungs. Fluids are all over the place. And you know that when you go swimming, if you go deeper underwater, you feel more and more pressure. That's why your ears end up feeling a little bit of pain when you go deep in water. So we're going to think about what kind of pressure will be felt by this buoy as we put it deeper underwater. Right now, the air particles in the buoy are open to the atmosphere, so the air particles are at the same pressure inside as they are outside. But once I seal this by putting water at the end, and then I put it deeper into the water, I can feel that there's a little bit of pressure being exerted on the air particles on the inside. That pressurized gas particles in there will exert a buoyant force on this buoy. You can see that I have to actually exert a force in order to hold it down. So we're going to learn about the buoyant force and pressure when we submerge an object in a fluid. The way how that we're going to demonstrate this is we are going to use a force sensor like we used previously. We're going to use a force sensor again today, so that means that we'll be using Logger Pro. We're going to start with an instructor kind of demo. You'll recall that if I push in on the force sensor, it reads a different force than if I pull out on the force sensor. And so for this first buoy, I will show you, I'll probably have Nate demonstrate it actually. I'm going to stick a little magnet in there, attach my force sensor to one end, and now once we submerge this into that water, we'll be able to feel how much buoyancy is pushing up against the force sensor. So Nate, would you help me out with a few things? First, can you lift that off just by holding the force sensor so that I can zero it out without the mass of the bottle on there? Right now, the force sensor is reading a downward force of 2.7 newtons. It's because it's feeling gravitational force down. Weight is pulling down on it. So I don't want to worry about that weight force. I'm just going to zero it out right now while Nate is holding it vertically. We're now reading a zero force. And also, just to make this a little bit more interesting, I am going to reverse the direction of my force sensor so that our numbers look a little cleaner. Alright, what Nate is going to do is he's going to keep that air trapped in that buoy and then submerge the buoy down to the black line that has been demarked there. And he's going to be careful to make sure not to let any air out. And he's going to be sure to only hold it by the force sensor if possible. Let a little bit of air out. Happens to the best of us, Nader. Can I actually have you remove it so that we get that air trapped in there? Now go submerge again, and you can kind of keep it pinned up against the corner. Good. All right, there you go, right there. And so now we'll collect some data. See how steady Nate's hands are. This is a fluid statics problem. Looks like you might have sneezed a little bit there in the middle. Good. All right, you're all set, Nate. And you can remove that, and we're just going to take the average. And what I want us to do is we're going to collect some data for now, and then we'll pull out our whiteboards and maybe plot it on Excel. So what we are going to think about is what will happen to the force that I read. So here's my force in newtons. For the first one, our average was 8.83. And we're going to think about how that force will change for different sized buoys. A smaller buoy, and then an even smaller buoy, and then an even smaller buoy. And our last one, our last little buoy that we're going to put in the water is this rod. So they're all marked at the same height, the same depth that we will submerge them at. And so we are going to think about the force versus the radius of our buoy. And for this first one, the radius of our buoy, I'm going to measure the diameter. It's about 13 centimeters in diameter, which means that the radius is 0.065 meters. Turn to your neighbor and take a guess at what you think is going to happen to this buoyant force as I get a smaller buoy and still submerge it to the same depth for each of these. Just hazard a guess, have a little discussion. What happen to the force as I shrink the size of my buoy, but submerge it to the same point? Go! Okay, you've got a guess in your mind. Let's see what's going to happen. Does anybody feel like being a volunteer and playing the role that Nate played last time? Let's get some students to see if they can step up in submerging these buoys.
I'll do it.
Mara, come on up. All right, so grab your force sensor and you can just kind of attach it to the other side of the bottle cap. There you go, nice, get it nice and secure. Good. Okay, hang it vertically please before you put it in there, and I'm just going to zero it. Zeroing, taking away the weight of the bottle itself. All right, it's your turn to submerge it. Do your best to keep all the air trapped in there, and once you get it to the line, I will start recording. You're a little below, so pull it up a bit. There, yeah. That looks pretty good. All right, I'm going to start recording. She's got steadier hands than Nate. You could be in LA, Mara. Oh, got a little less steady there at the end. She got nervous. Okay, thanks, good job. And I also want you, while you're at it, could you please measure the diameter of that opening? And I will get our mean value there, 5.8. 5.82 for the next buoy.
11 centimeters.
In centimeters, please.
11.
11 centimeters, which means that we have 0.055 meters. All right, great job, Mara. Who's next? August. This guy, August Hand, has got steady hands, I'm sure. Thanks. Thanks for that. That was a nice pity laugh. We'll take it. All right, please hold it vertically there. I'm going to zero it. Good. I'm just going to zero it one more time.
I don't think I have the steadiest of hands, I'm not going to lie.
Okay, now let's try submerging it to the line. Good. I think maybe a little up there, and now a little down. Yeah, good. All right, I'm collecting. How steady? The steadiest yet. He came here ready. His hands aren't sweaty. Confetti. All right, good job. Could you please measure the diameter of that? And I will transfer over the values. 2.68.
7 centimeters.
7 centimeter diameter, which is 0.035 meters. Great job, August.
Thanks, guys.
We got 2 more to measure. Who else feels like stepping up?
Sure.
Andrew, come on down. Please hold it vertically just by the force sensor, and I will zero it and hold it without moving. Okay, zeroing, enhancing. Good. All right, you are good to submerge.
The two-hand technique.
Yeah, the two-hand technique. Okay. Just worried about the gas. Good. There you go, right there. All right, we're collecting. Very steady, very focused. Wow. You want to be a dentist, right?
That's right.
You'll be good, dude. You'll be good. I would trust you to do dental work on me. Anyways, could you please measure the diameter of that one?
Sure. Didn't you want to be a dentist?
I did want to be a dentist. When I was 8 years old, I had a toothpaste-themed birthday cake.
Oh, no, you didn't.
I did.
Why am I-
Crest and Colgate were going at it.
Pictures of that?
They're probably out there.
They're probably out there.
You know, it's almost 6.
Okay, got it.
It's 5.8.
Okay, 0.029 is what we'll call the radius then. Great job, Andrew. One more, and it's the little tiny buoy. This rod right here. Zoe, come on down. Need you to hold it vertically like so. And we will zero it. Still. You actually are holding very still, so my joke didn't land at all. All right, you are good to submerge it to the line. Good, all right, looks good. We'll see how much force this ends up being. That's a very steady hand, and we take the mean of that. Could you get me the diameter of that as well?
Like 1.6.
1.6 centimeters, or 0.008 meters. Very nice. And 0.00. Yes, okay, good. All right. Do we have laptops? Let's have everybody pull out their laptop. Let's see. And if you don't have your laptop, you can work on the computer on the side. Let's try plotting this on Excel and seeing what we get. If it looks nonlinear, can you please try to linearize it?
Close enough.
Once you get a linear trend line, can I please have you get a whiteboard and put it on your whiteboard? We're going to do some calculations with it. All right, let's try coming together a little bit. So we are going to manipulate this somewhat. We are going to change this. So you should have force versus r squared. Don't forget to square your meters, and when you do that, you get a linear trend line starting from 0, giving you a specific math model that is F equals, your slope ended up being 2000-ish, right?
Yeah.
2020, okay, nice. 2020, you can think about the units as being the rise over the run, newtons per meter squared. And this variable over here is r squared. Our independent variable is r squared. So for our generic math model, we get F equals some slope times r squared. Does anybody have a guess at what they think the slope is? Mo?
Pressure?
Pressure is the exact thing that I was looking for. That's right. We're going to add a little something in a sec, but why did you think it was pressure?
Newton per meter squared is 1 Pascal.
Newton per meter squared is 1 Pascal. We should remember that a little bit. We saw that somewhat in the last PowerPoint, and now we're really going to hit it hard in this next week's unit. But there's actually something slightly wrong with this. I said that pressure is a force exerted over an area, not that pressure is a force exerted over an r squared. What would we have to do to this, the r squared value for this shape, in order to make it an area? That's kind of a weird way of asking the question, but Tyler?
Pi in height.
We would need to multiply by pi. So if we had a pi here, then that would be the area, and if you were to multiply by height, that would actually make it a volume. You would have the circular area, and then if you multiply it by height, you now have a cylinder with volume. So we are going to go to volume in just a sec, but for now, what I want you to do is on your Excel sheet, multiply all of those r squared numbers by a pi. So in whichever column that you have r squared, just take those numbers and also multiply by 3.14. So you should take your numbers, multiply by pi. We should get a new slope. What's the new slope? Anybody know it? Zoe?
643.
643, okay. Everybody make sure that you multiply all those numbers by pi and you still get a linear trend line. And now our math model turns into F equals that slope, and our independent variable is pi r squared. Or another way of saying pi r squared is the area, the cross-sectional area of our buoy. And this is the first equation of the day that we are going to derive. Pressure equals force divided by area. This is one of 5 equations for today. We will talk about a lot of the equations that were in the PowerPoint. It's a very unified class. So what we saw was that the bigger your bottle became, the more force you had to exert to hold it down, given the same amount of pressure. So if we submerge these all to 7.5 centimeters deep, they all experience the same pressure, but a greater force because the area is greater. All right, let's try doing what Tyler suggested. Tyler suggested that we could take these numbers, and if we multiplied by the height as well as pi, and keeping our r squared in the linearized form, if we do pi r squared h here, we now will have units of meters cubed. We'll have r squared, which is in units of meters, h, which is in units of meters. And so let's see what kind of trend we get and what kind of specific math model and generic math model we get. Generic math model, there it is. And I will tell you something about this depth that we submerged to. Each of these lines for every single bottle was 7.5 centimeters deep. Or in other words, h equals 0.075 meters. So take your numbers in Excel and now additionally multiply your column that has pi, r squared, and also multiply it by our number h. And we will once again get another linearized graph with a new slope. So now that we've done that, we get a linear trend again with a different slope. We get f is dependent on these variables. What did the slope end up being, August?
8579.
857.9 or 9? Okay, got it. Great. Thank you. Then I'll have units of newtons per meter cubed this time, so it is not a pressure anymore that we're measuring here. And our independent axis has pi, r squared, h right there. So my generic math model, I would have f is equal to some slope times whatever this variable is. Does anyone know a name for that variable, pi r squared h, other than Tyler? Bobby?
The volume?
That's right. It's the volume of buoy that we submerged underwater there. Now, 8,579. That's our slope, and it's not so easy as it was last time. We just looked at the units and said newtons per meter squared, it must be a pressure. But this time around, we got newtons per meter cubed. That does not clean up into anything nice and simple. In fact, our slope will be based on something about this system. Does anyone remember, every time that we've done an experiment in this class, the slope of the linear trend line always depended on something about our experiment? I've said it a couple times recently, and I wonder if anyone remembers. I recall Lillian saying it last time, I think, too. Tyler?
Constants?
It's the constants. You said it yes last class, I think, or 2 classes ago. Maybe I was wrong on that.
No idea.
Okay. The slope of all of these linearized trend lines are always based on what is kept constant in our system. Can you help me think, actually on your whiteboard, just brainstorm for me a couple things that are constant throughout the entire experiment, whether it was Nate or August or Mara or Andrew or August. Something was constant the whole time. It definitely wasn't the person holding the bottle. Can you please just jot some ideas down? What do you think could be some constants? Just write down at least 3. Right, absolutely. So we could call it the height of fluid, or we could call it the depth submerged. I'm just going to keep using those words interchangeably. And that we used an H for. That's one of the key ones that I'm looking for. Viscosity of the fluid is a very interesting one to try to pick on. I'm not going to write it down, but it is constant for this experiment. the viscosity of a fluid is basically how easily it flows. Like if it's really got a lot of resistance or friction, sort of like maple syrup or very heavy oil or grease or something like that, it's very viscous. And for this entire week and all of next week, we will assume ideal fluids, much like we said with ideal gases, which means that there is no viscosity. A very interesting discussion point for sure. Density is the answer that I was looking for. This will end up mattering for this fluid. So the density of the fluid, which we will use the Greek letter rho for. Pay very close attention to that symbol, and maybe even try drawing it once on your whiteboard so you can get used to it. The density of the fluid is definitely a very important idea for all of the next 3 weeks, so definitely spend some time reminding yourself how to do density. Just gonna make this box a little smaller so that I can squeeze in the next equation. There we go. Density tells you about the mass divided by volume. It's how much mass is taken up in a given amount of space, and we use the Greek letter rho, which looks a lot like a cursive P with a tail at the end, or maybe a tadpole for you marine science majors. The equation for density is mass divided by volume. And you will find that the density of this amount of water never changes. If it was a very, very hot day, the density would decrease because the water would expand a little bit. But for now, it is a constant. And in fact, for water, does anyone know the density of water? Like what number it is? Zoe?
1.
Rho equals 1. No units?
Hold on.
Not coming to you? Does anyone remember? Andrew?
Gram per cubic centimeter.
Gram per cubic centimeter.
You want that in SI units?
Thank you for heading me off. 1 gram per milliliter is the correct density for water, but it's not in the standard units. So in SI units, what should the SI units be? Alex?
Kilograms meter cubed.
Kilogram per meter cubed is what we need this to be in. Does anybody know how we could get 1 gram per centimeter cubed into kilograms per meters cubed? The answer brings us to 1,000. 1,000 kilograms per meter cubed, and you did say that right. So very nice. If you need help remembering how to convert between meters cubed and centimeters cubed, please carefully think about that. There's probably a homework problem. We've done that a couple times in class. There's one other thing that remains constant for this system, and I will remind you, maybe I put away my force sensor. I gave it to the other room. But we had our little force sensor, and it was holding this up like this. And then I always zeroed it. And then we always put this vertical thing here. And there's a reason why this pressure comes up, and it's a very common constant that we've talked about a lot in our lives. And when you say gravity, what do you...
9.81 meters per second squared.
Good. 9.8 meters per second squared. Just as a reminder, G we don't just call gravity, because then it's easy to mix up with force of gravity or energy of gravity. G is the gravity constant, or the gravitational constant. And that actually is going to be why we even have pressure. If we weren't on Earth, if we were in outer space, this water wouldn't be at the bottom of the container. It would just go every which way. It wouldn't have gravity pulling it down. And if it didn't have gravity pulling it down, we wouldn't have any water trying to find its way in there. And so really all of this entire experiment relies on us having a gravitational field of 9.8 newtons per kilogram. Given this information, you can see that our slope is based on some constants in our system. The height that we submerged it to was already outside of the line. It was our independent variable, so really it's already outside of the slope, so it will not be involved. And the slope of this, if we were to be really careful, should end up being rho times g. The density is 1,000, G is 9.8. We end up getting a number somewhat close to 9,000. I mean, it's a little bit off. We should have gotten 9,800. We got 8,600. This equation that we have right here is an equation for force versus the volume that we have submerged in an object. And this is called the buoyant force. Buoyant force, which is a brand new kind of force. We had 7 before, I think, and so now we have an 8th force. FB is the force felt when submerged in a fluid. And the equation for FB has FB equals the density of our fluid times G times the volume of the object that is submerged. That is our third equation for the day. Buoyant force equals rho G V. We proved that, we showed that we had a relationship between the force and however much volume we submerge it in, and it is dependent on those constants, rho and G. If I had a thicker, heavier, denser fluid like maple syrup or honey or mercury, then the pressure or the buoyant force would end up being much, much greater. And the buoyant force is what causes things to sink or float, because it's based on the density of this object compared to the density of the fluid that it's submerged in. So if an object has a density that is greater than the fluid, it'll sink. If an object has a density that is lesser than the fluid it's surrounded by, it'll float. And if its density ends up being the same, sort of like a balloon that has air filled in it with the surrounding environment being air, it should remain fixed in place. Its weight would perfectly counteract its buoyant force. One other note is that the buoyant force always points up. It will never point down. Just like gravity always points down, buoyancy always points up. It's the thing that causes things to float. And we are all experiencing a buoyant force right now. We are submerged in a fluid. We're surrounded by air. I can feel it a little bit around me. And so we should be feeling a buoyant force. Right. So since the density of the fluid that we're surrounded by is air, that density is 1 kilogram per meter cubed. 1 versus 1,000, which is what water is. So because the density of the fluid that we're in right now is so low, the buoyant force that we feel is also very low. On your whiteboard, I want you to draw for me 3 images of this magic bead bottle. Oh. You don't know what this contains, but I want you to draw this magic bead bottle exactly as you see it right now in its initial state. And then I want you to draw what you think it will look like after it is shaken up by me. And then once it has settled after it was shaken, we'll write down once again what it will look like. So I'll help you out with the initial. You should draw a bottle. And there are some white beads right here. Maybe you'll be a little bit more artistic than me. There's a bunch of beads there. There's some blue beads below it. And then there's also a little bit of fluid in there. And you can choose to add more detail or take more detail away, but I'm curious what you think it will look like after I shake it up. And then once it comes to equilibrium and settles down, what also will it look like? And then I'll give you a little bit of a follow-up on top of that too. I want you to guess what is inside the bottle. So let's make some predictions. Go. All right, I'm just going to take a brief look around. Some people say baby oil and water. What does that say?
Oil and water.
Okay. Nice. I read something different. Need to get glasses. It mixes up coconut oil, okay. Water.
A less dense.
Water and a less dense substance, okay.
That's a,
So what you may not realize is that there are 4 different substances in here, excluding the air. So we have air, we have one fluid, we have white beads, we have blue beads, and we have another fluid, actually. Let's see if any of your guesses were correct. None of them were correct on what will happen when we shake this up. So, let's give it a little shake. Get it nice and good. And pay attention to what it looks like now.
you were right.
Did you guess that the white beads would end up on top, the blue beads would end up on bottom, and there would be one layer of fluid in the middle?
No.
Doesn't look like it. And, oh wait, I wonder what's going to happen as
They
it
didn't give us a
They're
specific
going back.
time.
as it settles down.
It goes back.
Can you tell us what the beads are made of?
Sure. But polystyrene and a material called perler. So really, what we have here. I'll help. I'll add some pieces in a sec. I will never leave you. So there are 2 different materials, 2 different fluids there. When we mix it up, we get white beads on top. There we go. We get blue beads on bottom. And we get something in the middle. A little bit of art class for you. There we go. And then we end up getting the same thing in the beginning that we had in the end. Then, if you seem to think that you could have predicted this, can anyone explain what's happening? Like why it works like this? Have a short discussion with your group, and then let's see if we got any guesses. Talk for 1 minute. Try to figure out why it would do this. Perfect explanation, a great jumping off point. This is a density problem. It will matter about the density of the fluid and what the density of our objects are. If the density of the object is greater than the density of the fluid surrounding it, it will sink. If the density of the object is lesser than the fluid surrounding it, it will float. And so what we have here, anybody have a guess on what the materials are before I give it away?
I have 3 guesses.
All right, any 3 is good.
Vinegar, hydrogen peroxide, and isopropyl alcohol.
One of those is correct.
Cool. Is it isopropyl alcohol?
Yes, that is the correct one. Isopropyl alcohol. So one of those is isopropyl alcohol. Lily, do you have a guess on the other?
You said it wasn't water, is it salt water?
The other one is salt water, indeed. So it's salt water mixed with isopropyl alcohol. Can you guess which one is which?
Salt is on.
Salt water is on the bottom. Isopropyl alcohol is on the top. It has a lower density than salt water. I'm going to try to remember the densities off the top of my head. The density of the salt water, density of salt, H2O, I believe ends up being about 1.10 grams per centimeter cubed. I'm using the non-standard units. This is the density of the blue beads. I forget which ones those are. This one is about 1.05 grams per centimeter cubed. I think it's 1.03 actually. This one is the density of the white beads equals 0. I think it's 0. All right, I think this class session is going great. I love your participation. Let's pause and take a break, and we'll jump into our lab after this. I don't know what time it is, but I'll see you in 5 minutes. 3:15, I'll see you at 3:21. Let's get cracking on this lab. This is a really good one that gives super clean data. So please follow along with me.
I think it's great, actually.
Today's lab is called Under Pressure. And we are going to figure out exactly what dictates the pressure when you submerge in a fluid. So many of you swimmers might know that as you go deeper and deeper into water, that the pressure increases. Maybe you could feel that on your ears or in other ways. So we're going to figure out what actually is involved in that pressure. It's called hydrostatic pressure. So we will be using Logger Pro today, and that means that we'll need a computer person, and there should be one person who hasn't been on the computer out of this group so far. So please swap your seats right now so that the one new computer person can get on there. Okay, what we are going to measure is we are going to measure pressure, which has the symbol of P in units of pascals, and we are going to measure depth, submerged, or you could also call that the height of fluid. That is H measured in meters. So what we have here is a lot like the gas pressure. I thought I fixed my laptop, but I didn't. It's broken. All right, well, there we go. Good. All right. So what we have here is a lot like the gas pressure sensor that we had last time. We have a barometer, and it's attached to a ruler. And so what this thing will do is it will measure the pressure in the end of this barometer. So I need everybody to open up your computer, close anything that may have been on there previously, and then go find Logger Pro at the bottom. It's that one with the little calipers and the graph. Click it so that it opens up to this menu. And once you are there, have your experimentalist find the LabQuest Mini and plug in your barometer into channel 1. If it's not like hooked up, you know to unplug the power cord from the LabQuest and plug it back in until you have a green light. You should see pressure displayed in the bottom left of your program. Now my pressure is actually measured in inches of mercury, which is an extremely obscure unit. I don't know why this one does that, but I think all of yours should be measured in kPa, so I'll just make sure that I'm in kPa as well. Good. Everybody reading kPa? And you will see right now that this barometer is measuring about 100 kPa. Why would we expect for the barometer to be measuring 100 kPa right now, even though I'm not in a fluid? Haley? That's the atmospheric pressure. Right around 101,000 pascals is the pressure of the atmosphere. And just like when you go deeper into a pool, the pressure increases, that's actually true for the atmosphere as well. If I hold my barometer up at the top of the room, I'm reading 100.54, and if I hold it down at the bottom of the room, I am measuring 100.53, or 57, excuse me. So that is about a 30 pascal difference just from up here to down here. So now imagine how much the difference would be when you're flying in a plane at 4,000 feet. What we're going to do first before we do this is I don't want to measure the pressure of the atmosphere. I am just going to want to measure the pressure that happens only from the contribution of this fluid itself. So in other words, I need to zero our pressure sensor. Unfortunately, these barometers don't work as well as the other ones because there's not a zero button. It's missing from the top there. Usually it's just a nice little zero button. So what I want everyone to do, get your experimentalist to get that barometer right around the height of the fluid. Just kind of hold it near the top of the fluid, sort of like so. You know, we want it to be near the surface. And then for my computer people, what I need you to do is I need you to go to this thing in the top left where it says set up sensors. Please click on the pressure up there in the top left. Click that pressure in the top left. Go find your barometer, which is in channel 1. Click on the little barometer itself, and then in that menu there should be a 0 button. So click on the barometer, and then click 0. Once you're zeroed, you can put your rulers down. We can continue to talk for a sec. All right, so now I'm going to exit out of this menu, and you'll see that I have my barometer, which is just measuring pascals, and it's right around 0 pascals at the surface of the water. And what the main idea of the experiment is, we'll go into our notebook entry in just a sec, is you're going to measure the pressure at a certain depth, and then we're going to go deeper and deeper and deeper underwater to see how the pressure goes up. Everybody can see that the number is getting bigger over there. More and more pascals are being measured as we go deeper into the fluid. That's the main idea for the experiment, so let's just fill in the final pieces of our notebook entry, and then I will let you go. Okay. Our problem statement is, how does pressure depend on depth? In other words, how does P depend on H? I'm going to go over to the data table real quick. Our independent variable is height in meters, or depth in meters. Our dependent variable is P in pascals, pressure in pascals. And then we are going to list some constants. So this is actually a very similar experiment to the Poppin off lab, which is the one that we just did. I'm going to stay hip with the lingo. Let's think about some constants that will be the case for this. So think back to our constants in the last one. Does anyone remember something that was constant in the last one? Zoe.
Density.
The density of water. Do you remember what the number was?
1 gram per cubic centimeter.
And what was it in the standard units?
1,000 kilograms per cubic meter.
Good, good, good. Yeah, you got it. 1,000 kilograms per meter cubed. Those are always the units that you'll want your density to be in. There was one other thing that was constant. Well, 2 other things. Anybody remember what the other 2 things were?
The height.
We had height that was constant last time. Do you think that the height is going to be constant this time, Mara, if I take it and then I put it deeper and deeper for different measurements? I wanted someone to say this, but is that height going to be constant between this
Is the
and this?
the fluid's rising when you put the stick in? Is that what you mean?
Well, here the depth is 2 centimeters,
Yeah.
and that's like your first data point in this data table, and then you're going to go down to like 20 at some point. And so the height will be changing this time.
Okay.
Now, I did want somebody to say this. My main point is, it was a constant our last time because we always put them at 7.5 centimeters deep, but this time it is our independent variable and it will be changing, so it's not going to be a constant in this experiment. But I'm glad that someone said it so that I could go through that. What was the other one, Tyler?
Area and volume.
The volume, okay. All right, the volume submerged will end up being constant. I can get with that. That is not the constant that I was looking for. Mohammed.
Mass.
Mass? What mass are you referring to?
The stick.
Mass of the stick. Okay, sure. Yep, mass of the stick will definitely be constant. It won't affect anything about this barometer, though, and the density, and the fluid that is experiencing that pressure. But you're right, the mass of the apparatus itself is constant. Anybody got some other ones? Wow, Sam.
Gravity.
And when you say gravity, what would do you know the official word for that? Is it a force of gravity? Is it an energy of gravity, or is it a gravitational constant?
Gravitational constant.
That's the one. What's the number?
9.8.
What's the units?
9.8.
No problem. Anybody got the units? Fine.
Meters per second squared.
Meters per second squared, or you could have said 9.8 newtons per kilogram. There we go. Great suggestion. That is definitely one that will matter for this as well. And while these other suggestions are definitely good, these are the 2 that I want to make sure that we list explicitly. And so I will give you the free time to draw your experimental setup, however you want to draw it, whenever you want to draw it. And before we get started, can I have everybody please make a prediction for what they think the pressure in pascals will do as we go deeper into the fluid? And please make sure that you write an explanation. And you know what? If you guess that it's linear, can you please tell me what you think the slope will be based on? So let's take 2 minutes to do that, and then I'll send you off running. So just make sure that you get an explanation and a slope in there. I'll allow you to make sure that you finish that on your free time. And let me just show you one measurement that we can take. So I want for our heights to be something like 0.02 meters. And then maybe we'll go up 5 centimeters at a time. So you'll start at 2 centimeters deep and then maybe go 5, 10, 15, 20. Or, you know, if you want to get a bigger data point, some of you might be able to get 30 centimeters into the beaker. And I'll bring this back up in just a sec, but I want to show you how we would get one measurement from Logger Pro. So here, I have my barometer still at that level. It honestly looks like it could be re-zeroed, but... And so I'm just going to show you the 20 centimeter measurement. I will put this in at about 20 centimeters of depth there, and I will read off the number that I'm getting, 1.90 kPa. Maybe I went a little deeper there. 1.90 kPa is about what I have there, and so you just did one measurement yourself. Okay? So you collect your data using Logger Pro. Should be pretty straightforward, and then make sure that your computer person does the Excel work, and you are ready to begin. Any questions? All right, let's give it a go. So our graph, we should have writing with a pencil. We should have pressure versus height in meters, pressure in pascals, and we get a linear graph that pretty much starts at 0. You do not need to linearize. And so my slope, when I ended up doing this calculation and plotting it, pascals in PA versus H in meters, gave me a straight line from 0. My slope ended up being 9,800 pascals per meter. That was what I got. And sure, I'll say my intercept was 100 pascals. For your 5% rule, please, it's the end of the day, we're almost there. For your 5% rule, you should have some numbers here, 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 and here. So for our specific math model, I have pressure equals 9,800 pascals per meter times the depth H. And a lot of people have been having some thoughts about how to rearrange these variables, which are pascals over meters, to somehow match up with the constants of our experiment. You've made it to the end of the course, basically, and you know that this slope should somehow depend on what we kept constant on the front page. So what I would do to start this off is I would convert pascals. I would try to get to the most basic units that I can get to. Pascals are actually newtons per meter squared, and I have a meter that gets dragged along the way in the denominator. And then, so I'm just going to combine those. Before I break anything down any further, a newton per meter squared over meter is a newton per meter cubed. And then, a newton itself can also break down to be a kilogram times meter per second squared, that's m times a, and we still have our meter cubed on bottom. Now, I'm actually not going to do a simplification and cancel this out for a reason. I'll just take that number. Really, I have kilograms over meters cubed times meter per second squared. Sure, some of those could cancel, but just follow me on this for a sec. When I write it that way, it should kind of jump out at you of what variables actually are hidden away inside of our slope. I'm going to look back up here. I got something that's kilograms per meter cubed. That probably matches up with the density of water, which is kilograms per meter cubed. So this one right here is the density of water. And then I have something that's in meters per second squared. Sam helped us out with that one. It was 9.8. That's our G number. And so I have rho times G. units of my slope end up matching up with the units if I was to just multiply rho and g. So what was tricky about this is that many of you may have felt tempted to cross off this meter and turn this into a squared. And so now you're like, oh gosh, I got kilograms over meter squared and seconds squared. But it's actually really useful to just not cancel out those meters, because then it's really clear which constants are actually at play here. Okay. So if we scroll down a bit, and we get back here, now we can see that our pressure, capital P, is equal to rho g h. That is our official equation here that we get for today. And I'm just going to add a few more details. This pressure that we have measured is a special kind of pressure. It's called hydrostatic pressure. So I'll call it P hydro. Anytime that you are submerged in a fluid at some depth, the density of the fluid and gravity will cause you to feel a pressure. And so this is the official equation that you should have in a box that we just proved by taking measurements in class. That is hydrostatic pressure, which is a special kind of pressure that is pressure due to being submerged in a fluid. P hydro equals rho g h. So let's continue on. Meaning of the slope, I'm just going to keep my slope there because this is actually a very useful way to write the slope. We can say for every 1 meter of depth in a fluid, the pressure increases by, mine was 9,800 pascals, but that's because I idealized my numbers. If our slope is based on rho times g, it should be about 1,000 times 9.8. It should be about 9,800. I'm curious how close the rest of the room got. Let's start over here. What was your slope of your graph?
9671.
9671, which is extremely close to 9,800. Let's hear this group.
8864.
8864, 8,900 or so. That's more like what I was expecting. 9,200. 8,500. 8,500. 87. And 84. Okay, so our measurements tend to be a little bit low for the reasons that we sort of mentioned earlier. Really, a little bit of water does creep up into that tube. It's not a perfect measurement, but trying to get near 9,800 is what we were hoping for. Anywhere near 9,000 seems reasonable. And we can just say the slope is density of fluid times gravitational times gravity constant. That's just our shortcut way of saying what the slope means. Meaning of the intercept, we should say we expect an intercept of 0 because no hydrostatic pressure would be felt at 0 depth. In other words, if you don't go underwater, you don't feel the pressure from the water. When our depth equals 0, there's no extra hydrostatic pressure. If h equals 0, p equals 0. Okay, I'm just going to zoom out just a bit. All right, for this last one, I would quickly like to make a note in the diagrammatic model notes saying no diagrammatic model for this unit. It's basically a skip week. There's no special diagram. We'll get a new one next week. But I do just want to say that we can still use all the previous diagrammatic models that we've used. One that might be really useful is a force diagram force diagram for fluids. And if I was to just draw a cylinder like this beaker and think about the forces that were acting on the fluid, it will matter how deep in the fluid I am. So everybody draw me a beaker, a cylinder. And then I'm going to draw a square at the very top of fluid and a square at the very bottom of the fluid.
That's what it is.
And this, we're going to draw a force diagram for one that's at the very top and one that's at the very bottom. The one at the very top will feel a force of gravity just from its own weight, its self-weight. We all feel gravity right now because we all have our own mass. So gravity's pulling down on us. And the thing that holds this static fluid in place, it's at equilibrium, is an upward force called the buoyant force, FB. Depends on the density of the fluid and the volume that we choose to take. And down at the bottom here, we would feel the same set of forces, a force of gravity from itself, and also a buoyant force, FB. But all of the water above this bottom cube right here, all of that water right there, is also going to push down with its weight onto the cutout that we have, the little chunk of fluid. So I'm going to draw one more arrow pointing down that says force of gravity from water above. And since this is a static fluid, let's scroll up a bit, sorry about that. Since this is a static fluid, forces have to cancel. So I'm going to draw one more arrow, exactly canceling that. And that would be a normal force from the container.
So they'd be equal with the hash?
Yep. We got one hash here, we got one hash here, we got a double hash here, and a double hash here. Great question. Now I would like to reiterate that this is not a super precise force diagram. Usually the force diagrams are really quite telling. This is us sort of filling the space for right now because there's not really too many good ways of representing fluids with the old models that we have. Of course, you could still do energy charts depending on if the water's up high or down low. We'll talk about what happens when fluids start moving soon as well. Therefore, they would have kinetic energy. But for now, we're just going to stick with force diagrams. Okay,